Let me welcome. Oh. Um, Good evening. My name is Masahiro Mori, and I'm the chair of the physics department. And it is my pleasure to welcome you to this year's David Lee Historical Lecture in Physics. So before we introduce our speaker for tonight, there's one important tradition we'd like to attend to. That is to present this year's Morris and Gertrude Goldhaber Prize. And the Goldhaber Prize commemorates the work of Morris and Gertrude Goldhaber, who played a very important role in early 20th century nuclear physics. And we celebrate their legacy by giving 2 Goldhaber Prizes to the brightest graduate students in our department each year. The students are selected from those who passed the qualifying exam during the last year. And this year's prize winners are, number 1, Shannon Harvey. Now, where did I leave that thing? Okay. Congratulations, Shannon. And Shang Feng. Yes, Shang. Check here, okay?
Thank you so much.
Okay.
Yeah.
Congratulations for Shang. Now, let me give the podium to Professor David Nelson, who I believe was a PhD student of today's speaker. David.
Right. Thank you. So it's a great pleasure to welcome Michael Fisher, University Professor Emeritus and Regents Professor at the University of Maryland, and Horace White, Professor Emeritus of Chemistry, Physics, and Mathematics at Cornell University, welcoming here for a David M. Lee Historical Lecture in Physics. And it's great that Dave Lee could be here with us. It's the generosity of Dave and his family that has made this series of lectures possible for many years. Michael Fisher has been a towering influence for at least 60 years in many fields, including condensed matter physics, statistical mechanics, applied mathematics, and physical chemistry. With Ben Whittam, Leo Kadanoff, and Ken Wilson, he helped usher in the modern era of critical phenomena and condensed matter physics with anomalous dimensions, scaling, and the Epsilon expansion. He is a member of numerous honorary societies, including the Brazilian Academy of Sciences, the Indian Academy of Sciences, and the Royal Norwegian Society of Sciences and Letters, to name just the more exotic societies. His awards include the Irving Langmuir Prize in Chemical Physics, the Guthrie Medal, the Michelson-Morley Award, the Boltzmann Medal, and the Onsager Prize. In 1980, Michael, Leo Kadanoff, and Ken Wilson shared the Wolf Prize in Physics for their seminal contributions to understanding phase transitions and critical phenomena. Over the past 20 years, Michael has done beautiful work on physical biology. Remarkably, physical biology has also benefited from his pioneering work on statistical mechanics in the 1960s. For example, Fisher demonstrated via fugacity expansions the existence of non-classical polymer critical exponents. When applied to compute the bubble entropy for the classic Poland-Shiraga model of the helix coil transition, one could finally understand the DNA melting which underlies the polymerase chain reaction. Another of Michael's forays in statistical mechanics, the exact solution of the infinite spin, one-dimensional Heisenberg model, was later adapted to predict the forced extension curves in single-molecule DNA stretching experiments in the 1990s. Also, starting back in the 1960s and moving onwards, Fisher's work on critical point correlations laid the foundations, along with Whittam and Kadanoff, for the scaling theory of critical phenomena. Fisher is uniquely responsible for the prediction of the anomalous critical exponent eta. And I believe he once had a boat in Ithaca named the Eta, which controls the decay of correlations at the critical temperature. This exponent also plays a key role in quantum field theories, where it's closely related to the anomalous dimension of the vacuum. Perhaps Fisher's most brilliant work was his invention, with Ken Wilson at Cornell, of the Epsilon expansion, nothing less than perturbation theory in the deviation of the dimensionality from 4. Indirectly related to the concept of dimensional regularization in field theory, the Epsilon expansion led, almost overnight, to a huge number of essentially exact solutions to previously intractable problems in static and dynamic critical phenomena. The relative stability of various fixed points explained the existence of universality classes. Multi-critical points were introduced and classified. Scaling functions were calculated. The dependence of critical exponents on dimensionality and symmetry was finally understood, etc., etc. Although this revolution required the invention by Wilson of a new kind of renormalization group, Fisher's crucial idea of critical exponents in 3.99 dimensions is what brought this revolution to life. He's here to tell us today a bit about how this achievement came about with his lecture on Wilson's renormalization group theory, Ken Wilson, as I Knew Him. Please welcome Michael Fisher.
Personally believe that applause should be held to the end, if deserved. And so I would like to welcome you here, and this is the picture of Ken Wilson that I knew him, and I thought it would be nice to have a picture of Ken Wilson here. And this was a situation where he had too many papers on his desk. And that's the way I think of him. But he wasn't wearing a tie, and I think this is an exception because he had recently heard of the Nobel Prize. And so that's why he's wearing a tie. And the question I want to address is he certainly, what did he work at? And what did he learn from our association? And so he was at Cornell from 1963, and what did he learn, and why did he learn it? And what did he try out? And I'd like to tell you something about that. Firstly, the question of the exponents. So I've written only there, okay. The keep out is because the transparencies are no longer available. The projection for transparencies are no longer available. But I want to try and explain? Well, I wanted to explain the issue of critical points. And the first thing I'd like to show you is, and I have a special set of transparencies for these, are the critical point and how precisely it's defined. Yeah, that's, well, it doesn't fit, but you see it's there set up in microdegrees, and it's a very striking picture. Let me bring it down a little bit more. That's the specific heat of helium. Now, the question is, this is a microdegrees, and well, it's from minus 20 to plus 20 minus degrees. And you can imagine what happens if I increase the scale by 20%. And you see, if I bring it up, that it's still precise. So it's very precise, -1 to 0, and 1, that's 1 microdegree. And you see it's still fractional of a microdegree. So it's a very precise critical temperature. This is in helium, and it's very beautiful experiments. Well, what did I learn? What did we learn about that? Let me tell you a bit more. So I want to explain about the exponents beta and gamma. And I'd like to show you the exponent beta first. And that's a matter of behavior. And let's see. Oh, yes. Well, I'm not sure yeah. There's a button right here. Yeah, well, that's beta and that's gamma. Okay. And I hope you all knew it. So why did I put those up? Well, I put them up because partly this question of statistical mechanics. And the first thing, and I wasn't sure quite what people would know about the situation here. And so the first thing I'd like to do is to tell you, well, there are phases. And solid, liquid, gas. But at the point here is a critical point, and Tc, and I'll always using the notation small t is T minus Tc. And I will always be thinking about what happens when that tends to 0. Okay, so that's one point we know. And I've already convinced you that this critical point is a definite point. This was discovered by Andrews as you see, in 1869. And he's putting down there the critical point. Are we actually on 7?
I will check.
Yes, well, because we looked before, and we are on 7?
Yes, we are.
Okay. Well, I'm afraid you'll have to forgive me the fact that some of the critical points are coming out double, and some of the text is a little more than it should be. Anyway, the question is the liquid and vapor and liquid and gas become identical, as Andrews discovered. So back in 1869, the question was, can we understand this, and can we understand this from a theoretical point of view? And that's a bit of a question mark, and I wanted to show you this one here, which will, in fact, again, little t is going to be T minus Tc, and is going to approach 0. We're always going to be asking about the question of approaching 0. And the issue here is that if I think of the parameter in the rho liquid minus rho gas, that's the point at which the critical point exists. And so the question is, how does liquid and gas vanish? And it vanishes with an exponent beta. And so one of the questions is, what's the exponent beta? This point is that if I am interested in a magnetic system, I have a similar spontaneous magnetization. And I again can say, well, M0 vanishes as T to the beta. And M0 is liquid minus liquid gas. And I've put here the compressibility, and I put here the susceptibility. And I would like you to realize that there was no theory about this when the critical point was discovered. And the critical point was discovered originally, and the exponent beta was, well, there's a maximum. and that maximum is a quadratic equation, and that's the simplest form of a maximum. And that suggests, and the van der Waals theory was appropriate for that, that suggests that beta should be a half. Well, was beta a half? And the answer is certainly not. And I'd like to show you some evidence for that. So let's have a look at the evidence for that. And the evidence for that is conveniently summarized in this paper. And I think that shows the situation. The point there is that why is Schoen-Cienko in 1970? Well, this was the chemistry department, and one of the people in the chemistry department was Ben Widham. And he and I was also in the chemistry department at Cornell. He and I ran a seminar, and sometimes Ken Wilson attended that seminar. That's the point. And the question is, what did he learn? Well, one of the things he learned was that these experiments were done in 1970. Why were they done in 1970? Because here, these are metals in ammonia, sodium, lithium, and calcium in ammonia. And those are electrolytes. And so they were known to have a slope of a half. But Ben Widham suspected that this was only because you were further out. And if you look, you see that these are a set of parallel curves, and about 0.326. Not a half, not a third, roughly a third. But a third would be 0.333, and that was not the actual value. But and the experiments done by Schur and Cienko here showed the, again, T minus Tc, and again in 1970, and you see that there's a crossover in this electrolyte system. So the electrolyte system is peculiar, if you like, in the fact that it starts off looking traditional, but it falls into line pretty soon. Now, how about 2 dimensions? Well, I have an experiment here which tells me about 2 dimensions in the real world. These are beautiful experiments done by Moses Chan. And as you see, the point there is that it's 2 dimensions, and beta is not obviously a half, it's not a third, it's much smaller. So there's a strong dimensional dependence here. Actually, we know now 0.127 plus or minus 0.02 is rather a large uncertainty, but we know now that it should be close to an eighth. Well, an eighth, I remind you, is 0.125, and so this is remarkably close to an eighth. And this figure of 1/8 was discovered by Chen-Ning Yang. He said it was one of the longest and hardest calculations he'd done in his life. And he published it, and it was an amazing result. And it's vertically, as you see, comes down very vertically. Okay, so that was Moses Chan. Now, again, I would like to show you the susceptibility exponent. And these were experiments done a long time ago. And this is nickel. And these experiments were done actually in 1926. It was sometime later that I analyzed them in 1964, I think. In 1963, 1964. I analyzed them with Cuvelle, and he knew of these experiments. So these were old experiments, and they had been accepted as valid experiments. But they'd never been analyzed to say, well, what's this exponent gamma? The divergence of the susceptibility as I approach criticality. And as you see here, gamma is somewhere around 1 1/3, 1.35. And we would think it's a little lower now probably, but that's the sort of value. Again, not close to 1, which is the simplest theory would say. So not equal to 1, but 0.135. And these plots show you essentially the way of analyzing it. So let me move on. So the question I'm going to address is, well, still, what did Ken Wilson do and what did he learn? Well, the next development is that there were relations between these exponents. And this exponent relation, alpha plus 2 beta plus gamma equals 2, was originally from Ben Widham, and I'll put it that way up again, so you don't see the remarks I made on the side, but never mind. The point is, Ken Wilson certainly absorbed some of this. He absorbs the fact that the exponents were there and that they were independent of the simple theories. And I mentioned van der Waals. Landau had a general approach to these theories, and Landau was also wrong. Happily, he lived long enough to realize his errors and encourage Pokrovsky in particular to, and I mentioned Pokrovsky because he's with the same department that David Wilson is in. Okay, and so that's one of the issues. And so the question is, let's have a look at the Ising model, and let's have a look at the scaling. So the scaling functions, here's a scaling function, and well, again, tau is 10 to t minus tc, it approaches 1, and I've given there the scaled equation of state. And Widham in 1965 essentially said, well, look, the equation of state seems to be that the magnetization, and you remember the magnetization in the case of a gas and liquid transition is simply rho minus rho liquid, rho gas minus rho liquid. So again, it's very simple. And you see that I divide m by t to the beta, and what Wilson and what Kadanoff showed, well, and it was largely Ben Widham, showed that this could be written in a very simple form, namely t to the delta. And delta, of course, was related up here to alpha and gamma, and if you accepted this formula here for beta, it was simply the sum of the exponents. And so that was a question, and so we have to conclude that amongst the things Ken Wilson absorbed were the fact that there were Ising models, and the Ising model has this anomalous dimension. Now, there's also the anomalous dimension eta, and I was David Wilson kindly mentioned, David Nelson kindly mentioned that was one of the things that I was responsible for, and it's an anomalous dimension, characteristic somehow of the space. But who knows why it should be that form. And the n-vector model is when I start putting models together. Now, let me talk a little bit more about that. So the question is, do you need to understand, and I have no here, Okay. No, you don't need to understand quantum field theory to understand the renormalization group. And sometimes there's the theorists in quantum field theory, which you could say was the fundamental theory of particles and surely is important. Well, does one need to understand it? No, quantum field theory is neither the essence nor essential. On the other hand, if you know quantum field theory, it's a convenient way into this subject. Okay, so let's see what else we should see. Well, then there's the question of the anomalous dimension. And one of the books on field theory says that they have to be stressed, and they put great importance on this. And you see that in 2 dimensions it's a quarter, and that's actually something that you can show exactly. And you say, well, maybe it's twice an eighth, a quarter. Well, why no? We still have no understanding, really, of why it's a quarter. And if I go to 3 dimensions, well, it's 0.035, and we're not sure of the precise value. So we don't know any of these exponents precisely. They don't seem to be simple numbers, and they one of the Benfato and Galavotti in their book about renormalization group, and I don't entirely agree with them, because they are the ones that say, well, our own way to this subject was through quantum field theory, and therefore we write a book assuming that people know about quantum field theory. You don't need to know about quantum field theory to understand this subject. Okay, so this is some of the things that I believe that Ken Wilson did not need. Now, I mentioned the n-vector model, and let me talk a little bit about that. Because, okay, and we seem to be suffering again from, yes, the n-vector model. And I've done there the simplest model, and the simplest model is the Ising model, where the spins either point up or down. And this is a very handy model for thinking of gas-liquid, because there's either an atom there or not there. And it's either in a cell, and well, so you can divide space up into cells. The simplest cells are 2-dimensional squares, and I showed you the result in 2 dimensions, and I said, well, Chen-Ning Yang, had found that the answer was for a beta of an eighth in 2 dimensions. Well, all right, but what about more general models? So I can put up there the Ising model, and that's the simplest one, either point up or point down. But I can develop, if I allow myself 2 components, I can talk about the XY model. And it turns out that that is appropriate for dealing with superfluids and quantum mechanical systems at finite temperatures. It's not obvious, and by any means. Similarly, real spins can point in any one of 3 dimensions. Okay, the right, left, towards you. And that's the Heisenberg model. It turned out that as n goes to infinity, you have another model, a so-called spherical model. And that was an artificial model invented originally by Mark Katz. But there we are. And Gene Stanley also. If you go to n equals 0, you talk about self-avoiding walks. Well, polymers are typically self-avoiding because a polymer has a diameter. And that's normally, depending on the type of polymer, if it's DNA, then it's, as we know, it's quite large. But if it's a simple polymer, it's no more large than an atom, basically. And that's a few angstroms. So the question is, why should that be so? And the answer is, well, we don't really know, but we find out that that is the situation. Let me just rescue this one that's fallen on the floor. Okay. So I'd like to tell you the n-vector models. And this is the way we think about the situation now. Yeah. The spherical model here is for large n. So this is a dimension of n equals vertical. N runs from 0, where the polymer, if we turn out as n equals -2, you can have a Gaussian, and in a spherical model, you can have the large values of n. N equals 2, I've written here the name of Onsager, and he was the one who in 1949 essentially solved the model. People who came from Europe at the time were worried, and there were a number of scientists who came over to Europe, to America, and the question was, what has happened during the war? There were 5 years in which the Germans were not doing very much, and no contact was with the Russians. There were very few contacts. And so one wrote back to Europe, well, don't worry, the only significant result is that Onsager has solved the one-dimensional Ising model, the two-dimensional Ising model, and that is why Onsager's name appears here. Here appears the name of Kosterlitz, abbreviated, and Thouless, and they recently won the Nobel Prize, in fact. In fact, Michael Kosterlitz, whom I was at Cornell, and I've written 2 papers with, he won the Nobel Prize with Thouless, and recently, and he's actually talking about this result at the same time. It clashed with my talk. Here is the 3 dimensions you can say, well, we're really interested in. 4 dimensions and what happens above, I'll talk about separately. And so let me say that word of warning about the renormalization group. I've already said that. You don't really need to know about the quantum field theory. But let me talk about the limit of polymers for a moment. So let me show you what happens in terms of polymers. And I think this is, yes. So here's a polymer, okay, and I've drawn it there, and it's of length n. And the question is, what should I say about it? Well, one of the first questions is, how big is it? And I'm going to not ask that, but the question is, how many configurations should it have? And it turns out that I can think of drawing that in 2 dimensions as I've drawn there to you. And it's a self-avoiding walk. In other words, it can't cross itself. It shouldn't be in the same place at the same time because there are n bonds. And so no sites are revisited. And susceptibility coefficients turn out to be very similar. Okay. Well, the question is, how should you analyze this? And there I've actually put you up some numbers. And you can count this. There's the number of walks is 4, and 12, and 36, and 100. And it's a very large number. And so the question was, how should you analyze this? And this was something that I had learned from my mentor, Cyril Dom. And he said, well, why not plot the ratios versus 1 upon n? Yes. So these are self-avoiding walks and the returns, and I plot them versus 1 upon n, the ratios. Why plot the ratios? Well, why not? And what you see when you plot the ratios is versus 1 upon n, is that there's first of all a definite limit, okay, and there's a definite slope. You can say, well, there's some certain uncertainty with the slope, it goes up and down, etc. But the point is there's a definite slope. And there's a slope if you look at the returns. You look at the returns to the origin. And these should have been, again, without crossing themselves. So these are self-avoiding walks, and these are returns. And you can ask, well, why is there anything special about them? And the point is that Cyril Dom was the one who pointed out that if there was just singularity there, so you remember that the specific heat had a sharp spike, and the susceptibility diverged to infinity at the critical point. And so why should there not be a simple power law? Well, it was Cyril Dom, whom I knew from London, who originally he was at Oxford, who pointed out that the slope gamma is in front. And if it was a simple divergence, a simple power, then there should be just mu to the n, asymptotically. But if there was something different, then there was a gamma. And that was one of the things that showed up. So that's, again, here is a slope. By the time you think about these things, there are, in more sophisticated methods, you can analyze the slopes with, and the inhomogeneous approximants is just a particular mathematical device for analyzing these slopes. But the simplest thing is to take the slopes. And the slopes then define a gamma, and there was something clear. Now, one of the things of Ken Wilson that we soon learned was that he was very much in favor of computation. And this paper here is a paper he should really have been a co-author on, because he essentially did the calculations for my student. And my student then analyzed it in a way that I would put. So I've added Ken Wilson's name here because he got some of these tables. And I've taken a table there from the paper just to give you an idea of what he should have done. And okay, so that, but now I should talk about Ken Wilson himself. And his vision, he attended the seminar, and every now and then he said, he would like to talk. And this is one of the things that I came. This is his vision of a flow. And one of the parameters is, I couldn't understand this. This was clearly part of his vision of approaching the critical phenomena. And he imagined flows in space, and I'll tell you later on what space it was, but at this stage, it's important to appreciate half-formed ideas. And so you should carry this around with you and say, well, that's an idea, and let me think of it in more concrete terms. Well, what is going on here? So what's important, what I've said, is a tolerance for incomplete understanding, okay? But here he has some initial smoothness. So his picture was that, well, I arrange here, this is, let's say, the temperature. And as I vary the temperature, so the system varies. Well, there's one particular temperature that goes to a fixed point, and then he imagined the flows were diverging, and some of them went off to the left, and the low temperatures, and some of them went off to the right. And as you see, this was what we got out of. This was all I got out of his lecture. Okay? And this was essentially what he had said, was conveyed. He was not the clearest of speakers when he was developing his ideas, but this was his idea. Now, then at one stage he felt he had been scooped by Kadanoff, and Kadanoff had an interesting idea, and it's worth talking about it. So Kadanoff, let me bring that down. The question was he felt scooped by Kadanoff. Well, scooped means somebody else has had the great idea. But it turned out that Kadanoff looked, and Kadanoff had assumed that if you, and this is the illustration, if you reduce the squares and rescaled them, let's say in this case by a factor of 4, you started with a system of spins, let's say the Ising model, and in each site there was a spin up or a spin down. And then he assumed that rescaled the deviations. Well, he assumed essentially that you were doing the same thing. And this was not really acceptable, but the crucial idea of rescaling space was one of the things that caught Ken Wilson's attention. And one of the crucial ideas of Ken Wilson was embodied in Kadanoff. And that's probably why Kadanoff won the Wolf Prize. And I should say that when Ken Wilson won the Nobel Prize, as I heard from my sister, the first thing he said was, what about Wilson and who was he? How about Fisher and Kadanoff? Because he'd shared the Nobel Wolf Prize with us. And he said to my daughter, he rang up when he told, and they said, well, are you turning down the Nobel Prize? And he said, no, we're not. But that was the answer they gave. And he called up my daughter, so she tells me recently, and said, well, will you tell Michael that, call Michael to the phone? And she said, no, I won't wake him up to say he hasn't got the Nobel Prize, but that you should say it. And so it's interesting that Ken Wilson thought this should be mentioned. Now, I'd like to say here some of the things that he did, but essentially he was not scooped because Kadanoff method essentially assumed that the form was the same. And if you assumed the form was the same, then you could explain it, and the idea of the reduction was important. So let me just show you another point here. Let me put down this on. So Kadanoff postulated essentially the Widom relations, and he predicts scaling, and you get some relations. But the question was why, and so I've written here, and let's see if that works. Okay, so no, he was not scooped by Kadanoff. Okay, but he felt he was, and he felt that Kadanoff had a crucial idea, and as Kadanoff had. So, But why? And well, I've written divide and conquer there, and new interactions must enter. As soon as you actually try and do this, you find that, well, there should be 4-spin interactions. How about that? And so you have a reduction, but the new interactions must appear. And so Kadanoff had not had any intersections with this. But if you take this literally, reduction, then you must say, well, at very least there will be a 4-spin interaction. And as you go on, there must be further interactions. And so you can't just reduce this scale and say nothing has happened. But that's what essentially Ken Wilson did. And so how to select the degrees of freedom so appropriately. So that's the issue. And so how to select these degrees of freedom? Well, the way Wilson did it at first was momentum shell renormalization. So he said, well, let's think of a Fourier space, and we were already physicists knew that Fourier space was very important. And in Fourier space, you ask momentum shell, and so the Q is X and QY. This is again for 2 dimensions. And the suggestion of Kadanoff was that left over in the Wilson's momentum shell renormalization group. So Wilson suggested that you should integrate over this shell. So the red dots mean that those are the ones I integrate over, and the net result is a change of scale. And so that's, and you can write here, and so RB stands for the renormalization group, B stands for the reduction in the scale. What was the 4 in the case of the Kadanoff thing I showed you. And you could imagine B as being large or small. Later on, Wilson solved the Kondo problem. The Kondo problem was a problem of understanding a magnetic impurity in an otherwise non-magnetic system. And to understand the magnetic impurity, this had been a major problem in condensed matter physics. And so it was advertised as such. And Ken Wilson then solved it. I would say that he got remarkably little credit for having solved it. And people who had said, well, it's a major problem and so on, suddenly evaporated, and they didn't thank him for the solution of it. But he essentially solved it, and as you see, he used onion-like spherical shells and the location of the wavefronts. He explains in a RevMod Phys article. So Wilson eventually wrote a number of papers by himself, and he explained this, how he solved the Kondo problem. And well, I said I would show you this, the space in which he, let's see if that's appropriate. So, what is the space? Well, the space is the space of Hamiltonians. It's a very general space, a lot too general, and nobody had thought about it before. But Wilson convinced one that this was the natural place in which to think about what was going on. So you put any possible reactions down, and these are going to show up in the space. So a capital H there with many dimensions is the dimensionality of the space. And it's of the interactions, of the possible interactions. Okay, So normally one can only measure the field and the temperature, and that's why the first plane is the plane of temperature and magnetic field, because that's all you can measure. And so you can think of that as a plane, a physical manifold, but then you can do the renormalization group. And you can iterate that, and if B1 is the first scaling and B2 is the second scaling, then RB1 and RB2 are acting. And this then shows what happens. And I'd like to essentially say that this is the picture that I carry around from Wilson. Namely, there's a space in which you flow, and the flows are, there's a fixed point on the flows. And you can ask about the flows. And supposing here you had the system of sodium and ammonia, and there's a critical manifold, and here and there are the trivial fixed point and the high temperature fixed point and the low temperature fixed point. So this is the part of the way of thinking about things that I said you had to accept and partially understand. So it's important to partially understand this, and this is the way I think of it. And essentially what he says was there's a critical manifold and you look for a fixed point. And if you down here have water and over here you have nickel, that's a different fixed point. So nickel, there has to be a room in the space of all possible Hamiltonians for all possible interactions, and therefore all possible materials are going to be in this same space. And this picture is the way I think of what renormalization groups were set up for. So let me see what else I have to say, because there's one important, I don't think I will talk about that. There's an important issue, and that is how one goes further. And so I was talking to Ken Wilson at one time, and this was before he had solved the problem, and I would like to read something that I wrote here. I would like to read and it's a negative thing about two Italians. And maybe I shouldn't read it out aloud, but I think it's looking into the past now. And these two Italians one was De Castro and one was Ionellicino, and they claimed that they had anticipated somehow Ken Wilson's renormalization group. And I've already mentioned one of the crucial things of the renormalization group, but in 1969, word reached Cornell that two Italian theorists, De Castro and Ionellicino, were claiming that the multiplicative renormalization group, as expounded in the field theory text of Bogolyubov and Shirkov, could provide a microscopic formulation. So they were claiming that they'd solved the problem. And, the bottom line was, had they? And we invited De Castro to Cornell, and I walked for lunch, and I remember this rather vividly, with Ken Wilson afterwards. We walked to lunch, and that day it was a pleasant lunch, and a good walk, and it was a nice day. I mention that because Cornell is in upstate New York, and often it snows and there's rains also. So the weather is not as good as it is here, but you can judge that for yourself. Okay, so I proved, I said, what had happened And the formalism and content of the field theoretic renormalization group was totally unfamiliar to most critical phenomena theorists. So we listened to that. But I believe that the impression that De Castro and Renormalization left, that they had anticipated Wilson, was totally wrong. And I have a vivid memory of walking to lunch at the Statler Inn, as I said, and you remember the Statler Inn. And I asked Wilson, well, did we hear anything new? And of course, by new, I meant an insight into what was going on. And the conclusion of our conversation was no. And the point was of our misunderstanding. And we hadn't learnt anything. And so to be fair to Renormalization and De Castro, they later on published a review in the Dom Green series, and they were pretty honest there. They said what was wrong with their earlier. But nevertheless, you should beware of claiming an important result if you have done nothing toward it. And and now, at least, I was talking about this at Aspen, and as some of you know, there's Aspen Center for Physics, and amongst the people in the audience was Murray Gell-Mann. And Murray Gell-Mann had actually been the thesis advisor at Caltech of, believe it or not, Ken Wilson. And so he said, yes, but tell me, what was all this got to do with the work that Francis Lowe and I did so many years ago? And that was a renormalization group, and that was one of the first papers. So I always was upset that Ken Wilson had used the same name. But in response, I explained the connecting thread. It was a far-reaching thread. It was a thread, but to believe its length was comparable to that reaching from Maxwell and Boltzmann and the ideal gases to Gibbs' general conception. And it's worthwhile saying that Gibbs was a great theorist and a great American theorist, one of the first American theorists who was brought up here, and he operated at Yale University, not Harvard, I'm sorry for that. But he was a great perception. And if you go back to the ideal gases, well, you can see the thread that leads to Gibbs. But it was one, long one. And basically, Murray Gell-Mann couldn't see what he had done to inspire Ken Wilson in this way. And that was the story that I thought was amusing and that you would like to see. Okay, so let me move on. And again, walking to lunch, and I had been away for a year, and I was walking to lunch with Ken and talking about his expressions. And he had already got this renormalization group, and the question was, so what could you do with it? And if you accepted the fact that there was a renormalization group theory and a renormalization group that shrunk things down, then you could say, well, that's solved it. Well, it hadn't solved it because you couldn't compute any of the exponents. And so then we got talking about the dimensionality. And dimensionality has always been something that intrigued me. And I'd already learned that if you look at polymers in a large enough dimension, and you might say, well, there's two-dimensional polymers and there's a three-dimensional polymer, why bother any more polymers? Well, if you're a theorist and intrigued by dimensionality, you say, well, what about 4 dimensions and what about 5 dimensions? And it turns out that there was a theorist in chemistry who had already thought about that. And one of the things you learned was that in 4 or more dimensions, polymers behave as if they had no exponent. They behave simply, okay? And they just behave as n to the n, where n is the number of polymers, and the power, big N, is the power that you would associate with them. It's mu to the n, if you like. And there's no exponent. So I should show you again this exponent of Cyril Dom. But you remember the factor that was in fact of an n to the gamma minus 1, that was absent. And so the question was, well, what should you do about it? And I made the suggestion that since I knew that 4 dimensions was likely to be the highest dimension at which there were really exponents, and admittedly you can't get to 4 dimensions, okay, so you can't do more than 2 or 3 dimensions in reality. You can't do experiments in 4 dimensions. But I suspected that in 4 dimensions there was a limit. And that I suggested, well, how about a small parameter? And that led to a paper that I show you here, critical points, critical exponents in 3.99 dimensions. This was a paper written by Ken Wilson, and he was kind enough to, where he wrote the first draft, and I had made the suggestion, and that's why I was a co-author. And he was essentially religiously putting the authors in alphabetical order, and so I was the first author. But I insisted that he was the first author, and and incidentally, he did make it plain that this was my contribution, and I was not to expect to collaborate with him again. So I'm grateful for that, because I was then applying to well, let's see if you look at here's the susceptibility exponents and the anomalous dimension, and there is what the exponent was, and this is where we thought we had an expansion. So notice the dimensionality starts here at 4 and then runs down. So 2 and 3 dimensions are here and 5 dimensions are here on the left. And so this is the epsilon expansion, and this was gave people an opportunity to compute. And let me show you some of the results that they obtained. And I think that's here. And let me pull this back, and let me see what else. So this is to the 3rd order, and as you see, this is I've reintroduced the n parameter here, and the Ising model, you remember, is Ising model equals 1. 0 is for polymers, and minus infinity is for, and as you see the exponents, you can check as n goes to infinity, that's 1 plus a half epsilon, and epsilon being 4 minus d, and you can see that it all makes sense in the spherical model. And so here's and I mention here epsilon to the 4th and epsilon to the 5th because the Russians were very hardworking, and some of the Russians have computed actually out to epsilon 5th and epsilon 4th and epsilon 5th. And so these exponents have been carried further. And, well, you can ask what you do with that expansion. And this, very quickly, Ken Wilson wrote a separate phys.rev letter. And the exponent phi takes some mentioning. you said there was a button here, didn't you? The exponent phi. You might ask what this is. Well, again, notice that it has a definite meaning as n goes to infinity. And this is the exponent eta that I talked to you about, and that Galavotti and co. in their book said was especially important. And this is and that's n plus 8. So that goes to 0 as n goes to infinity, whereas this goes to 1, well, a half. And if you look here, there's an n cubed downstairs and an n and an n squared and an n cubed upstairs. So these already work, and you can check the results for the spherical model. The spherical model is a peculiar model. So the question is, what is this phi? Well, if I have an Ising model, an n equals 1 model, and I think of that as an n equals 2 model, as a special case, then there's a crossover. And as I can add a potential that would be n equals 2 and n equals 1, and this crossover exponent tells you, well, does that matter? And the answer is, well, you can see it is a positive exponent, and so what you learn is that if there's a hint of a higher symmetry, then that plays a role, and that's important. And so that's I'd like to show you. Well, at the time, I would like to now show you some photographs of Ken himself. And here's a photograph of Ken, which I think you will recognize more closely. And this was on learning of the Wolf Prize. And as you see, Ken didn't wear a tie normally. And he only wore a tie when he won the Nobel Prize. That's my... and of course, he won... I was wearing a tie. I usually wore a tie. I'm wearing a similar jacket now. As you see, I'm not wearing a sweater because it's warmer here than it was in Ithaca at the time. Okay, so this is on learning of the Wolf Prize, and that's really what more Ken looked like. He was rather shy. He was not a man of many words. Is that not correct? You were interacted with him as a student. And he was a shy person. He had a wife. Yes, and you might ask, well, how about that? Well, he married her when he got the Nobel Prize. And we had Roald Hoffman in our chemistry department who had already got the Nobel Prize, and he urged Ken not to worry about it. He said, well, they'll invite her anyway, and you can take her. But that was still the impetus that enabled Ken to marry Alison. And he married Alison, and I would like to show you one of his things that he enjoyed doing was folk dancing. And so here he is in a...
Slide it down a little bit?
Yes, let me slide it down. That's a bit better, isn't it? Yes. Well, it's still... But you can see that he's wearing a kilt, and he was interested in folk dancing, and he folk danced with his wife, and that's Alison Brown. Cornell was rather stupid because he would have liked a better job for Alison, and Cornell should have given her a better job. They finally went off to Ohio State and eventually retired, and eventually he died rather sadly. But I'd like to show you a couple more pictures of Ken. And, okay, this is one for, and is that showing well? Yes. Yes, pretty well. But I'd like to say something about him. He was a builder of intellectual bridges, and he had passed on other ways of exploring physics. And this is partly why his ideas were difficult to understand. He'd gone on rather different paths. And so I already mentioned his conception of a space which was hard to understand, of all possible interactions. And, well, that was a space in which he was a builder. And I would like to read something that was written by my colleague David Mermin about him. And let's see if I can find it. Yeah, I think I have it here. So in those days, Mermin writes, Mermin, by the way, knew him when he was at Harvard. His father was a famous chemist, E. Bright Wilson, and at one stage his father called me up and said, well, I know you know my son, Ken, because by then he'd already become famous, and I'd interacted with him, and he knew that I'd interacted with him. But he said, not quite his words, but I have another son, more normal than Ken. Because Ken was by any means unusual. And this son was David Wilson, and he was a biologist, and I knew him at Cornell. And so Mermin writes, well, Michael Fisher and Ben Widham ran a very lively weekly seminar on phase transitions. It started at lunchtime and went on until everybody except Michael was exhausted. That's me. The only allowed medium of communication, well, I still think that's a good idea for seminars, was the blackboard. It forces people to slow down and say what they want to say. And occasionally people would say, well, I want to show some data. And I would say, well, give me the data ahead of time and I'll make a Xerox of it. And we can see whether the theory still agrees with the data at the end of the day. So there's but in 1996, a preprint arrived from Kadanoff. And I volunteered to give a report on it. This is David Mermin writing. And I remember my title, My Early Impressions of Kadanoff's Partial Justification of Widham's Conjecture on the Homogeneity of the Equation of State Near the Critical Point. So it's quite a long title, but I didn't allow abstracts. And so you could have an excuse of a long title. And I still believe in that. I think a long title and in the absence of an abstract. As I studied it, it struck me as a sloppy piece of work. This is David Mermin writing. He started with a well-defined problem and then proceeded to butcher it, replacing detailed local configurations by gross averages, making unbelievably crude approximations to force those averages to look like the original problem, and then repeating the whole messy business over again. So this is Mermin's impression of Kadanoff. In those days, there was a wall between particle theorists and condensed matter theorists that was rarely crossed. But to my surprise, Ken showed up for my talk, and even more to my surprise, he appeared in my office a few days later. And evidently, he seemed to take Kadanoff seriously, as I've already stressed, because the crucial idea was this shrinking of the space. And if you like, and about a week later he showed up at my office ostensibly to talk about Kadanoff's paper, but what he actually had to say was that the crucial thing about the whole business was to think of a ball rolling up a hill with just enough energy to get to the top of the hill. Well, if you work on that, I understand that. I don't. I admire you. And That's the crucial piece, exactly the story. I humored him and said, yes, Ken, very nice, Ken, as I ushered him out the door. This is Ken Wilson writing. Okay, David Mermin writing. And he says, well, he mentions then what is the character of Mermin, Ken Wilson really was. And he writes, well, we had a wonderful professor of mathematics at Cornell, Mark Katz, and I personally owe a lot to Mark Katz because he invited me for a year in 63, 64, by which time he was not at Cornell. And he famously said there are two kinds of genius, the ordinary and the magicians. An ordinary genius is a fellow whom you and I would be just as good as if we were only many times better. Okay. So that's something one of the beauties of doing theoretical physics is you realize there are a lot of people that know more than you and are brighter than you and have better ideas than you do. And that's a valuable idea. But there's no mystery as to how his mind works. An ordinary genius is a fellow whom you and I would be just as good as if we were only many times better. There's no mystery as to how his mind works. Once we understand what they've done, we feel certain that we too could have done it. Okay, so mostly in theoretical physics, that's what you learn. We too could have done it. It is different with magicians. They are in an orthogonal complement, okay, of where we are. And the working of their minds is, for all intents and purposes, inconceivable to us and incomprehensible. Even when we understand what they have done, the process by which they got there, and that I'm not claiming to have explained that, okay? I'm just explaining my part in it and the role of it. But their working of minds is, to all intents and purposes, we understand what they have done, the process by which they have done it is completely dark. Mark was 20 years older than Ken and me, and although he clearly admired Ken, he was suspicious of the theory of renormalization group. And it was Kadanoff's partial justification. Mark was wrong as I was wrong. And this is the crucial thing. Ken Wilson was a magician. It was a privilege to have known him. And I would like to finish up that with my statement there, that it was a privilege to have known him, and he was a magician, and very different. Thank you.
Well, as Michael said, Ken Wilson was a man of few words, and I'd just like to relate that I went to a seminar where Ken was expounding one of his very deep and abstruse theories, and there was a tremendous bolt of lightning and clap of thunder, and Wilson paused, looked out the window, and said, "Did I say something wrong?" So Michael has had a very long day and entertained us with this beautiful talk. I think he would be willing to answer a few questions, and we have microphones on the right and microphones on the left. So if Michael would permit, maybe we could have a few questions, please.
Yes, I'm absolutely happy to answer any questions. And if there are no questions, that means you've understood everything I've said.
So I would like to start with a brief question, if I might. In that remarkable paper on critical exponents in 3.99 dimensions, there is a calculation which I think you might have suggested of coupling together two Ising models so that there would be a limit that had an XY character. And this was one of the first cases that I know of, maybe the very first, where you had a spontaneous generation of a symmetry. The cubic perturbation at quarter-quarter went away. Now, did you in fact suggest that calculation?
I think probably I did,
Right.
but I'm not sure because essentially, as I explained, Ken explained that I was not to collaborate with him thereafter. And that was fair enough, because I had plenty to do, and I had my students do it. But so I think probably I was responsible
The Baxter
for
model, the
yeah,
analogy,
bringing
and that sort
in.
of thing, right?
I think probably I was right.
Okay. Everyone in this audience has understood absolutely everything, evidently. Yes, please. There's a microphone coming, Dudley. Right.
I thought I'd like to ask if he played chess with you or any other physicist at Cornell.
No, as far as I know, Ken did not play chess. And I think he was too busy to play chess.
Well,
I should
you
have
would
said...
probably have, the games would probably have been very short if you played them,
Yes,
because
maybe. But I
his
should have
father-
said that he was interested in computation.
Yeah.
And that was one of the principal things he did. And that's why later on, he was interested also in science education. But
Yes.
computation was his primary interest. And believe it or not, he was a computer expert. And as I explained briefly in this paper with Tarko, he'd done all the calculations. My student had not done any. But we, having done the calculations, well, so what? And we worked on the so what.
I asked because I thought you might be interested. His father was my PhD mentor, and I knew Ken when he was in high school and on. But Bright Wilson, his father, said that he used to play chess with Ken, but he quit doing that when Ken reached 6 years old because he beat his father so easily.
Yeah, I think I've no doubt that he was very good at chess, but as I said before, I think he probably decided that it was a waste of time.
Arup Chakrabarti, please.
So you said that Wilson loved computation. I know that in the later parts of his career, he spent a lot of time trying to work on smarter ways and faster ways of doing quantum chemistry. Do you know what he concluded from all of that years of work?
Well, I think he was somebody who was apt to tackle hard problems, and if he'd made no progress, he was going to claim he'd made no progress. And so we did talk about, I do remember one or two of his seminars claiming that he was going to think about chemistry, and partly to justify his father's interest. But he gave one talk about that, and he said, well, the problems were harder, and the chemists had made more progress than he'd given them credit for. And so I think he gave up on that one. But he was very interested in computation generally, and was in fact appointed to run the Cornell Computer Center. And that's one of the tragedies of Cornell in a way. They didn't take advantage of that and promote his wife and so on. But anyway, that's my belief.
Question.
I have a question about the epsilon expansion. So in particle physics, we work in 4 minus epsilon dimensions, and then we take epsilon to 0 at the end to get something back in 4 dimensions.
That's right.
How do you feel about saying something about 3 dimensions from expanding around 4 and taking epsilon to 1?
Well, I mean, you have to look at what the series is saying. And my belief is that there are various ways of doing it. That's why I mentioned the inhomogeneous differential approximants. So the differential approximants are a way of dealing with a series. So I would say that if you remember that we could fit it in 2 dimensions. So we knew the answer in 2 dimensions. So that if you were starting at 4 dimensions and you then went down to 3 and 2 and fitted it at 2 dimensions, to the answers you knew, then there was a reasonable chance of that you were within order. Well, you can estimate some uncertainty in 3 dimensions. So I would say that's a perfectly good method of proceeding, provided you don't claim too much accuracy. So always the question is how much accuracy you claim.
Okay, if there are no further questions, let me just say that I believe there's a reception up in the physics library. And let's thank Michael once again for his wonderful historical lecture.